Well, so welcome you all to the next session of S.J.Sarkar's Fundamental of Electrical Engineering demonstration. So, what we had discussed about the Kirchhoff's law and how we could apply Kirchhoff's law in different circuit, why KVL is actually going to fail, and why KCL is a much more easier solution in comparison to KVL. We had discussed in the previous videos. Now, what we are going to continue the discussion, we would be starting the network theorems in the today's video. So before going to that, so let us try to understand the two terms. The two terms which are very common. One is circuit, another is network. These two terms are widely used in our electrical arrangement, and they are often used interchangeably, but they are not the same thing. So what is the difference between that? Let us try to understand by using this sort of graph. Let us suppose I am having 4 cities A, B, C, D, which are interconnected in some fashion. Okay, now let us suppose my purpose is to move from point A to C and then return back to A. So what is the most easiest option? I could go to follow this path and then come here. So it would be something like this. Through B I could get, or what we could do, we may directly ignore this B to reach here. So I may go in this way and then return in the same path, or else if I am going in this way, I would be returning in the same path. So although I can start from A reaching at C, returning back to A, this arrangement in electrical system, we can't consider it to be a closed path because there is no loop in it. Similarly, this system is not having any loop. Now let me take a different path, that I am going from A to B, then B to C, and then taking this return path. So what I could do, I am going like this and returning by this. So you could see that there is a closed path there. So this is a classic example of any network. Rather I could say this is a classic example of a circuit, and these are basically network. Now let us take a different example. Let me go from A to B by this path, then I am going say B to D, then I am going back to C. So I am taking different path now, and then from C I am going to B and then returning back to A. So I would be taking this path. So whether I could consider this to be a closed path, you could see that this loop is closed, this loop is closed, but B is common there. So there is a intersection here. So this I can consider it to be a closed path. And I could say that this is a separate closed path, this is a separate closed path. So this is a circuit, this is a circuit, and the entire section, it will be a network. So if I am having that sort of idea, if I am going to apply the same here, so what I could see, that there will have a current flow here, there will have a current flow here, but there will not have any current flow here until and unless I am connecting some resistance here. If I am connecting some resistance, then it is going to have some current flow. Now if we don't have this one, So there is no current flow here. So I could say that this is a circuit because it is having a closed path. This is a circuit, it is having a closed path, and as a whole the entire thing will be a network. Now, if I am connecting the resistance here, say I am connecting RL here, so it now no longer become a network, it is going to remain a circuit. So from that I could understand that circuit is basically a closed path and network may be closed or may not be closed. So what we can say that basically this network is a superset of circuit, because it might happen that multiple circuits are forming a network, and in the network some of the loops might not be complete, it might be open as well. So in practical scenario, what we can say that railway system, we are calling it network because there are a few places which are not connected. Say you could see from point A to C, although there is a movement may be possible, but that is not can be considered as a closed path. So that's a railway network is an example of network in practical system, and our blood circulation system is an example of a circuit, because you could see we are having the heart, we are having the organ. So from heart to organ, organ to heart, we are having different artery vein combination to have the blood flow from our heart to the organ and organ to the heart. So it is an example of a circuit. Now, if we are having any arrangement, if it may be a circuit or it might be a network. Let us take this example only. It might be a case that this R1, R2, R3, R4, Vi, all the parameters are constant. And what is actually variable? This RL is actually variable. This RL is variable. So what if we could do that instead of this particular arrangement, if I am having a black box with two terminals coming out, let us suppose this is a black box and there are two terminals where basically we are having RL, and this RL may be variable. Then if you have to find out what is the current passing through RL or what is the power dissipated in it, so we could compute it very easily if we could have the black box in a much simpler arrangement, in some series parallel combination with some voltage source or current source. If I could represent this entire arrangement, this section actually, if somehow I could convert it to the black box, then the computations are going to be very easy. Although we know what, that if we know KCL and KVL, then we can apply it to any circuit to get the desired value, whatever be the voltage or current or power, whatever we want we can find. But in such case where this load resistance is variable and the other things are remaining same, so for that type of arrangement, network theorem will be very useful to serve the purpose, because we are doing what? We are actually framing the remaining portion to form a black box, which is basically now a network because their terminals may be open, and then if we require, we are going to connect the variable load resistance here and find the value for different value of RL. So that is what basically the significance of this network theorem is. So here also we are going to apply the knowledge of this Kirchhoff's voltage and current law. But the objective is to develop this black box, how I could develop the black box. So basically this network theorem is used for circuit simplification. Now we are going to discuss a very popular network theorem that is called Thevenin's theorem. So what is happening over there, that let us suppose I am having some arrangement with some load RL. So what I had said, that generally the objective of this network theorem is to have the black box. So what is being happening here, that this section, what we are doing, we are converting this into a very simple arrangement comprising of a voltage source and a series resistance RTH. This is VTH, Thevenin voltage source, RTH is the Thevenin resistance, and this arrangement is basically, I could say, that the Thevenin's equivalent network corresponding to this one. So how to find out that? VTH is also called the open circuit voltage. So basically what we are going to do, we are going to open circuit the load terminal and try to measure what is the value of the open circuit voltage, and that is what is basically the value of VTH. And RTH is the equivalent resistance as seen from the load terminals while deactivating the sources. Deactivating the sources implies we are going to replace the source by its internal resistance. Ideally, a current source will have infinite resistance and a voltage source will have a zero resistance. So what we could do, we could actually open circuit this current source and short circuit this voltage source. So from this arrangement we could directly find out that this RTH will be nothing but the series parallel combination. So R1 and R2 will be in parallel, R1 parallel to R2, and that would be in series with R3. So this is the value of RTH what we are going to get. Now we have to find out VTH. So in a very simpler way we can apply Kirchhoff's voltage law or Kirchhoff's current law. Now what we have seen that generally if you are going for KCL, then the number of variables are lower because the number of branches are generally more than the number of nodes. So let me apply KCL here. So what is going to happen here? We are going to take this at 0 volt. So this node will be at 0 potential. This will be 0 potential. Now in this particular node, let us suppose this is node number 2. This point is at 0 potential and I am talking that this voltage is VTH. So we could say this node voltage should be VTH. And in node 1 here we are applying or we are having some voltage say V. Let us assume that we are having some voltage V at node 1. And let us assume the direction of current. So let me suppose this is I1, this is I2, this is I3. Okay, so we had assumed the direction of current and we are applying some node voltage. So now applying the KCL at node 1. What is going to happen? We can write I1 is equal to I2 plus I3. So what is I1? That is basically V1 minus V by R1. V1 minus V by R1. That is equal to I2. V minus 0 by R2 plus V minus VTH by R3. So now if we are going to rearrange the thing, we are going to get something like V into 1 by R1 plus 1 by R2 plus 1 by R3 minus VTH by R3, that would be equal to V1 by R1. So let us be equation number 1. Now this V and VTH are basically the unknown quantities and remaining are the known quantities. Now we are applying the KCL in node 2. So in node 2 what is happening? I3 plus I should be equal to 0. So I3 plus I should be equal to 0. Because I3 and I, they are incoming current and there is no outgoing current. So what is I3? It would be V minus VTH by R3. It becomes V minus VTH by R3 should be equal to minus I. So what we could write? V by R3 minus VTH by R3 should be equal to minus I. Let us be equation number 2. So we are having two equation 1 and 2. We are having two variable V and VTH. So solving that, we could find out that there will have some value of VTH. Now once VTH is known, we had computed RTH, so we could develop this particular circuit. Now when we are connecting some RL here, so what will be IL? IL will be VTH by RL plus RTH. So that is how basically this Thevenin's theorem is going to work. We are having an arrangement. We are finding out the Thevenin's equivalent network. Means this is the Thevenin's equivalent network. And then we are connecting the load terminal to find out the current, or if you want to know what is the power loss, we are going to compute it. So that is what the point is, and that is why the necessity of this network theorem is for simplification of the arrangement. So if anyone have any doubt, you should ask me without any hesitation. I am stopping here for the time being. In the next video, we will be discussing about another type of network theorem, which is the Norton's theorem, where you could see that we are actually going to replace the entire circuit by a current source and the resistance Rn. So what is it, how we are doing, that would be understood in the next video. So thank you. Have a nice day.